This video will show you how to make graphs when the function is of this form. In other words, you're learning these parent graphs when it's y equals 1 over x to the n, where n is a positive integer. Never negative, because that one makes sense. Like 1 over x to the negative 2, we would just write that as y equals x squared. So n will be a positive number, and we'll restrict it to integers for now, so it's easier. These are often written as 1 over x to the p to remind us p stands for positive number. We're specifically looking at cases where it's a positive integer. Because we're dealing with fractions, we should review some fraction arithmetic. The fraction is of the form 1 over a, so the numerator is a constant fixed value. The denominator is a variable we could plug in different numbers for it. Okay, this notation means if a gets closer and closer to 0 while remaining positive. In other words, if you have values like 1 over 10, 1 over 1, 1 over 0.1. So look only at the denominator. The denominator is always positive and is getting smaller and smaller and smaller, closer to 0. This is the idea of looking at a limit, which will be one of the bases of calculus. So 1 over 10, 1 over, so this is 0.1, this is 1, this is 10, this is 100, and this is 1,000. So look what happens to the fraction as a whole if we let the denominator get bigger but keep the top constant. The fraction as a whole, I let the denominator get smaller. I said that wrong. So we're letting the denominator get smaller, get closer and closer to 0 and positive. The fraction as a whole gets bigger. So as the denominator approaches 0 from the right, meaning from the positive numbers, while remaining positive, but the denominator in black ink here is getting closer and closer to 0 while staying positive. If that gets closer and closer to 0 from the right, then the fraction as a whole gets bigger and bigger and positive without limit. We can make this smaller and smaller, and the smaller we make the denominator, the bigger the fraction gets, and there's no end to it. If we want a fraction to be a million, we can do that. If we want it to be a billion, billion, trillion, billion, we can do that. We can find a denominator small enough. Okay? In the same vein, if we let the denominator get closer and closer to 0, but with negative numbers, this is called from the left, we get this sort of thing. So this is negative 0.1, negative 1, negative 10, negative 100, negative 1,000 for the values of the fraction as a whole. We're letting the denominator get smaller in absolute value. Now some people, especially if you've only taken math classes and not really used this in a science class like physics, they'll say, wait, the denominator is getting bigger, not smaller. Well, you want to stop thinking that way, because in physics, for example, if the denominator is representing a velocity, this means 10 miles per hour to the left, 1 mile per hour to the left, a tenth of a mile per hour to the left. So these are smaller and smaller speeds, and the negative sign only means to the left. Very frequently in science, the negative sign does not mean small, it just means something else, like the sign of a charge. For example, electrons have a negative charge. That doesn't mean the charge is smaller, it's just a different type. Or the negative can mean left or downward for a falling object. So in physics, we talk about these numbers actually getting bigger and with just negative. So more and more negative, bigger and bigger in absolute value while staying negative. So as the denominator approaches 0 from the left, meaning the denominator is negative but it's getting closer and closer to 0, then the fraction gets bigger and bigger without limit but negative, bigger in absolute value. Okay, finally, what happens if the denominator increases? So here's our fraction, 1 over a. If we let the denominator increase, then the fraction decreases. For example, look at these denominators, 0.1, 1, 10, 100, 1,000. The denominator is increasing while the numerator is staying constant. This is 10, this is 1, this is 0.1, 0.01, and 0.001. So look what's happening to the fraction as a whole. If we let the denominator get bigger, the fraction as a whole gets smaller. So as a, the denominator increases without any end to it, okay? The number's in black ink. Okay. Then the fraction as a whole, this means approaches 0, gets closer and closer to 0. It never actually can get there. There is no number you can put in to make the fraction as a whole 0, but this means it gets closer and closer to 0, and there's no end to it. There's no line you can draw and say it won't cross this. Okay, as it approaches 0. It can get as close to 0 as you want. If you want the fraction to be 0.00 with 100 zeros and a 1, we can find a denominator big enough to make that happen. So this means the fraction as a whole gets closer and closer to 0. Same for negative denominator. Negative 1, negative 0.1, negative 0.01. These fractions as a whole are getting closer to 0. Okay, so now we're going to use that idea. And first we'll look at graphing y equals 1 over x squared. In other words, these are fractions where n is even. The exponent is even. Y equals 1 over x squared, and the graphs for y equals 1 over x to the fourth, y equals 1 over x to the sixth, etc., they all have the same basic shape. Okay, and what is that shape? Well, we make a table of values here. When x equals 0, y can't exist because that would be divided by 0. Okay. When x equals negative 1/2, you would square that, get 1/4, but then it's 1 over 1/4, so that's 4. Since it's an even exponent, you get the same result when x is positive 1/2 as you do for x equals negative 1/2. So we have that coupling that we saw with the in the previous video. You get these pairs. Notice as x gets bigger in absolute value, right? The absolute value goes from 1/2 to 1, 2 to 3. Y gets smaller. And y is always positive because we have an even exponent. And we've graphed that here. The dots are the integers here. The 1, 2, and 3 are 1. Well, x equals 1, x equals 2, x equals 3, evenly spaced. And you'll notice the corresponding y values here, here, and here, their change between them is not equally spaced. So you get a curve. As x gets smaller, here's the x is 1/2, y gets bigger. So you get this graph. And on this side, you get the same graph but a mirror image. The y values are positive when x is negative. Okay, this is an even function, which means it's symmetric across the y-axis. We saw that in the previous video. As x approaches 0 from the left, in other words, as x approaches 0 while being negative, that means from the left like this, the y values, up and over, up and over, up and over, the y values get bigger and bigger and bigger. They increase positively without bound. Okay? As x approaches 0 from the right, as you look at these x values and go like this with your pen from the right, the y values up and over, up and over, up and over, again, increase without bound. As x gets bigger and bigger and bigger, this arrow, positive infinity, means as x increases positively. In other words, as you do this with your pen, okay, the y values decrease. They approach 0. They can't ever reach 0, but they get closer and closer to 0. That's what this arrow means. You will use this arrow in calculus class, so you're being introduced to it now. Okay? Same thing if x increases negatively. Gets bigger and bigger and bigger, but negative, the y values approach 0. So as you go like this, in fact, we'll use the right colors. As you go like this on the x-axis, notice what happens on the y-axis. They go up and over, so when I'm 1, I'm there, like that. So as the blue pen, the x values become bigger and bigger but negative, the red pen, or the y values, gets closer and closer to being y equals 0, but it can never actually reach it. It just gets closer and closer and closer. So that's when the exponent is negative. The same thing applies, or that's when the exponent is even. The same thing applies for larger, even exponents, as long as you have the single term like this. No negative signs or anything to flip the graph. It always has this basic shape, so you should memorize that shape for this type of function. Y equals 1 over x to an even integer. Okay. The y-axis is a vertical asymptote, which means if you draw with your pen, you get closer and closer to the y-axis, but you never actually touch it. The x-axis is a horizontal asymptote, so as x gets bigger to the left or right, your pen comes down and it gets closer and closer to the x-axis, but never actually touches it. All right, so now let's look at odd integers for the exponent. And of course, the simplest odd integer here is a 1. So we're going to graph y equals 1 over x, but the same basic shape will apply to 1 over x to the third, 1 over x to the fifth, etc., as long as it's an odd exponent. Okay, so we have the same numbers as before, but now look, the pairing, since it's an odd exponent, has a negative and a corresponding positive number. So when you're in quadrant 1, when x is positive, the y values are positive, and you're in quadrant 1, and you get the same basic shape as before. The numbers are, of course, different from the previous graph, except right here at 1, 1. But it's the same basic shape. As x gets bigger, y gets smaller. As x gets smaller and approaches 0, y gets bigger and bigger and bigger positive. Now, when you go to negative x values, the y is also negative, and so the graph has been flipped down into quadrant 3, and you get this basic shape. As x approaches 0 from the left, y gets more and more negative. as x gets bigger and bigger and bigger, but going to the left, y gets smaller and smaller and smaller. The y value approaches 0. All right, you should memorize this as the graph for 1 over x to the odd integer. All right, and finally, to sum that up, if y equals 1 over x cubed, 1 over x to the fifth, etc., okay, this is an odd function. Okay, symmetric about the origin. That means if you pick corresponding points, like let's say, I didn't do the best graph here, but let's say you pick 2 1/2 and -2 1/2, they'll be connected by a line that goes through the origin. 2 1/2 and -2 1/2. Okay, this is for the graph y equals 1 over x. Okay. Corresponding points where the x value has flipped its sign, the y value will also flip its sign, and that line connecting them will always go through the origin. It's called symmetric about the origin. Same thing as before. I don't think I have to go through all these. I think they've been explained. And the y-axis, again, is a vertical asymptote because your pen approaches it but never touches it, and x-axis is horizontal asymptote.